My name is Zoran and I come from the University of Belgrade. I teach artificial intelligence and computer programming, and my expertise are neural networks. During the recent popularity of deep learning techniques, I decided to try to adapt the Neuroph framework. That's a neural network framework in Java that I founded, that open source project, and to adapt it to try the deep learning algorithms. So during this session, we are going to do a quick walkthrough to the basics of deep learning, and then I will show you how to use Neuroph to implement deep learning algorithms. So in order to adapt the content, I would like to ask you how many of you are familiar with neural networks? Can you please raise your hands? Okay, nearly half. So I will just make a very brief introduction. And how many of you are familiar with general machine learning principles? Okay, pretty much the same. So I will skip this general thing, just some brief info for those who are did not have opportunity to work with those technologies. So what is deep learning? Deep learning is actually rebranding neural networks because it is a better way to sell them now, because they have ups and downs like every technology. They've been working and they have huge expectations, and they figure that they cannot use it to solve some problems, and now suddenly it has become possible to use them to solve some interesting problems, especially in computer vision domain. So you probably heard about research that is being carried on in Google and Facebook by Professor Jan LeCun and Hinton. And they are using deep learning architectures to mainly create computer vision algorithms to detect objects, to recognize faces, to try to classify image, and things like that. And it is also very interesting that those same principles are starting to being applied to other domains, for example, language processing. And the basic idea is to try to use them as a general learning algorithms. So it might be possible, it might be not, so we'll see more details later during this session. So the most popular type of deep learning algorithm is so-called convolutional neural network, and that's the one that we are going to see here today. And the reason why it is so important, why everybody is so excited, because it requires less pre-processing and manual feature extraction. So less preparation of data, and it also provides better accuracy than any other methods that have been used for computer vision and optical character recognition problems. Another type of neural networks also are autoencoders. They are being used for feature extractors, dimensionality reduction, and also like additional technique which can be combined, for example, with the multilayer perceptron type of neural networks to get better results. So as I said, these all algorithms, we'll take a look more about them later, are mainly applied to computer vision problems and other high-dimensional problems. Because you see, for classification problems, you have support vector machines which are pretty good, but when you come down to image recognition, which is huge number of inputs, you're using color information as input, typically, neural networks are much better. And another thing that's new is that people actually managed to create a hierarchical feature representation. So with convolutional networks, you can kind of guess what's going on, which is very important things, because very often neural networks can be observed as a black box. So it works or it don't works. So sometimes it's hard to guess why it's not working. Now, a few words about the Neuroph. As I already said, it's an open source neural network framework in Java, and it provides not only framework, it provides also a development environment which is based on NetBeans platform. So you have IDE-like environment for building various type of neural networks. Also, you can easily take those small set of base classes and create your own new types of neural networks, and that's exactly what we are doing here now. We are using the core classes from the Neuroph to create deep learning architectures. So, also it's worth mentioning that Neuroph won the Duke Choice Award 2013, and on the official website, you have a link on slide. You can download the source code, jar files, and there's some lots of documentation and examples and tutorials about how to use Neuroph. So before I start more into deep learning architectures, I would just like to, for those who are not familiar, to make a gentle introduction to multilayer perceptrons, because both convolutional networks and autoencoders are basically multilayer perceptrons. They are modified, customized versions of multilayer perceptrons, and they are using a backpropagation learning algorithm that's being known for quite some time, for about last 20 years. So, in order to show you how multilayer perceptron works, I'm going to run through a quick demo. We are going to create a multilayer perceptron for classification problem. What you see on the screen now is a wizard in Neuroph Studio that you create a sample for multilayer perceptron classification. So in this wizard we can easily create some problem, let's say a diamond data set. Okay, so what you are looking at now here is a diamond data set. You see blue dots in the inner side of the diamond and the red dots all from the outside. If we take a look into the data set, you will see a list of randomly generated numbers in this space, and if it is red, it is outside of the diamond, and it is inside of the diamond, it is 0, so blues and reds. Next, we can create a neural network. Let's say to choose a multi-layer perceptron architecture with 2 inputs, 7 hidden neurons, and 1 output neuron. So this is that neural network. Now, what you can see, neural network is, to put it simply, a graph. It is a graph that can calculate. You feed some input into these input nodes of the network, and then it transfers that inputs to these hidden layers. And each of these units, so-called artificial neurons, does some simple calculation and pass it to another layer. So the learning of the network comes to feeding the data through the network, calculating output, then comparing the actual output on the network with the desired output, which is a classification class, and calculating an error of the network. And then using error minimization procedure, which adjusts all those connection weights between neurons. So Neuroph is interesting because you can easily visualize different aspects of these networks. So let me see, you can say display preference and show weights and weights highlighting. So you see each of these numbers, each of these connections has some numbers assigned to it, and you can inspect all of these neurons and their connections. You can see what's actually going on, kind of. Also, you can inspect each individual element in this properties window and see, let me see, where is the properties, yes. You can see to which class in the Neuroph framework each component provides. So it's a nice visual tool. You can get idea what's going on inside. So the neural network is not a black box anymore. You can see its internal components. So let's back to this example. In order to start training, you just need to drag and drop the data set to this field. Okay. Okay, we already did that. The data set is visualized. Then drag and drop neural network. And that's when you say, I'm going to use this data set to train this neural network. And by clicking the train button, you start training. So we are going to put this maximum error, the error threshold, when the network will stop learning, very low, so we can observe what's going on. So, as you can see, this is this total network error going down, and in visualization window you can see how the network has put borders around this data which represent a diamond. Now, what's going on? So we already explained, we are feeding network with data and correcting the total mean square error, but what's interesting is to take a look at this view. Now, this is what is going on in the hidden layer. So this is layer neurons between the input and the output. These lines, network is creating regions. And how it is creating regions? It is creating regions by using these lines. Each of these lines, straight lines, correspond to some of the one hidden neurons. So you see, the neurons are dividing input space, and network is combining all those divided regions. So this is nice to see and visualize in 2 dimensions, because you can put it here. But if you have high dimensionality, if you have, I don't know, for image, you can have 1,000 of inputs and hundreds and thousands of neurons and hidden layers. That's very, very hard to visualize. So it's a multi-dimensional space. So we are not going to talk much more about, so just going to, because the error is very low, it will never end. That was intentional. We are just going to stop learning now. And that's how Neuroph can be used to create neural network using wizards. Now, you get the idea how it looks like, what's the end result. Now, one important thing, okay, this is, okay, block you already seen this, I showed you how it looks like in Neuroph. Now, how it looks when you want to use that in code, okay? Let me show you here. To create a multilayer perceptron in Java code, you just need to use multilayer perceptron class with using simple constructor. The idea of creating Neuroph is to put the power of neural networks into the hands of mainstream Java developers. You don't have to be expert for neural networks or machine learning to use Neuroph. You can just get familiar with basic Neuroph API and create an instance of neural network. Of course, you need to know what are these parameters, and this, in this case, corresponds to number of neurons in input layer, in hidden layer, and output layer. Next things that you have to do is that you have to import some data set. Okay? Usually, you import the data set from a CSV file. So there is a very convenient method, create from file data set, a static method, which creates data set from file, and you just provide file name, number of inputs, number of outputs, and the delimiter character. And then the last step, when you want to train the network, you just invoke the learn method of the neural network class and provide a data set as an input parameter, and that's it. Of course, it's not always this simple. You need to know a little about the problem, you need to choose architecture, to guess architecture, to be honest, and then you need some tweaking that is also very easy to do. You just have setter methods to tweak everything that you usually need. And at the end, when you train the network, when training stops, you can save network, you can serialize network to a file as a Java object, and then you can very easily load it in your application. You just provide a reference to Neuroph jar files, and you load it from the file. The next example will show you how to use trained network and saved network. You just have static method create from file, which expects input parameter file in which network has been saved, and you create an instance of neural network. And there are basically 3 methods. You have set input, you set some external input to network, which is usually in the form of a double array. You have calculate method, which calculates the entire network, and then you just get an output vector of the network. So basically what the neural network does, it does mapping between some set of inputs and some set of outputs. So this is the basic introduction to neural networks and Neuroph. And before we move to convolutional networks, I would like also to explain few things before. You see, the traditional, so-called shallow architecture for recognition, let's take, for example, image recognition, always include this pre-processing and feature extraction step. Okay. For example, if you want to do recognition of faces, you have to prepare images of eyes, okay? You have to prepare images of mouth, of nose, of some typical features that you want to detect. And also, you need to do a lot of pre-processing, like normalization of the contrast of the color to make the images invariant to those changes. This is very, very time-consuming and very error-prone process, and but the result and quality of the recognition will depend a lot of this step. And then you feed that data to a trainable classifier, which is usually some general task-independent classifier. You can use SVM, you can use neural networks, anything you like. But the thing is that those classifiers are not specialized for those type of problems. And that's the thing when convolutional networks come into game. So how many of you is familiar with image convolution? So very few of you, so I explain it a bit. So image convolution is a technique. You have a basically sliding window which goes through entire image, and that sliding window is a small matrix, okay? Small matrix, it can be 3 times 3 or 5 times 5, or it can be of any arbitrary size depending on the problem that you're dealing with. And you know, all those filters in the Photoshop, you know, when you want to try to make grayscaling, you want to make it black and white, you want to detect edges, you want to make it a neon glow and everything else, it works on these principles. You have a small matrix that goes through the entire image and multiply pixels and generates new image. So that's how image pre-processing is done. And you see this step here, pre-processing and feature extraction, is usually done by using image convolution. So Jan LeCun was smart enough to figure out that he can combine the technique that he was doing manually and put multilayer perceptron in the front. And okay, it worked. But the new thing that convolutional networks brought is actually that they figure out that they can train these filters, these convolutional filters, using backpropagation algorithms. So now you don't have manually to prepare the feature extraction and preparation, pre-processing, but you can train the network to adjust, to adapt those filters. So this is how the typical convolutional network looks like. It has many more layers, much more neurons than multilayer perception that usually does, and each of these layers have specific role. So we'll go through those to explain. What it is doing, beside filtering, convolutional filtering, it is doing kind of template matching. So template matching is you move the slide along the picture and you're trying to figure out the region with the maximum activation, the region which gives the maximum output. That region has the highest similarity to the pattern that you are looking for. So you're matching a pattern. Again, it is a small matrix. And in the terms of convolutional network, it's called kernel. Okay, so that's a kernel. In this picture, you can see an input layer, which is usually an image. So you can get raw color information from image. You can have even 3 layers, okay? One for each channel, a layer for red, a layer for green, a layer for blue color information. And then you have a set of layers who are called feature maps and some subsampling layers. Okay, feature maps are just doing plain convolution. Okay, they are using a kernel which goes through the image, and each feature map detects specific feature. So as you can see, this first set of feature maps, each feature map detects specific features. So one first can detect eye, second can detect nose, third one can detect mouth, okay? And the thing is, depending on the size of this kernel, the next layer will be always smaller than the previous one. So what's actually going on? You are going to reduce dimensionality of the problem while it's going through each layer. So that's what feature maps are doing. So they are doing convolution, and next layer, which are called usually pooling layer or subsampling layer, they are doing template matching. They are trying to figure the maximum output of the each feature map layer. Okay, so you did convolution. You have searched for certain pattern during the entire image, and now you are going to see which pattern of all those has a best match. So this is what subsampling layer is doing. It tries to find a region in the image with the maximum activation. After that, you put it through another convolutional layer. After that, you can stick as many as convolutional layers you like, but you should be aware that it can slow the execution or learning, more important, learning of the network very much, and it can even make things more complicated, so network never learns. So there are no guarantees that neural network is going to learn the data, so it requires lots of experimenting. There are different variations. Some people don't use these subsampling layers at all and say, okay, it's much better when you're just doing convolution, but it's very much problem dependent, you know, depends what you are doing, and it also depends how did you prepare data. So you have a set of feature map layers and subsampling layers, and at the end you have simple multi-layer perceptron. Okay, so this layer here, just on output, is just this multi-layer perceptron. You can have several layers, but it's usually enough to have one. And the interesting thing is that you're using the same algorithm for adjusting all those weights as you're using for multi-layer perceptrons. There are some variations, and usually you don't use backpropagation to train those subsampling layers because they're just looking for maximum. You're using backpropagation just to train the multi-layer perceptron output and the feature maps. At least that's what we figured out it works. Okay, so there are many. We are talking here about general principles. There are many implementations of this type of architecture, and this one is what we have tried, and we figure out that it works. So how do you create convolutional network with Neuroph? It looks very complicated, right? But in Neuroph, it can be very simple when you know this introduction, how it is composed. You have a convenient convolutional network builder, okay? And you can use to edit convolutional layers and feature maps and create network very simply using convolutional base. So very simple network is to add one convolutional layer, okay? We specify the convolutional kernel. That's the size of that window that we are going to scan image. And this number 2 is saying, okay, we want to have 2 feature maps, okay? One is going to detect eye and the second is going to detect nose or whatever. I skip this one. This here is input dimensional, okay? Input dimension says what is the size of the image usually. If you have image 20 times 20, then you need 400 pixels, 400 inputs. Or if you're going to go with full color, then you're going to need 3 times that. That's 1,020 pixels. And in this network, we just put one convolutional layer and put this fully connected, which is output layer, okay? And we just create that network. So to show you the full example, this is that very basic example that shows that this convolutional network learns and that it works. So we are creating this input layer dimension 5 times 5. Okay, we have 25 pixels in total, and we are using a small kernel scanning a window 3 times 3. Okay, and here we are creating convolutional network, specifying input dimensions, saying with this convolutional kernel size, we want 2 feature maps, and we add fully connected layer with 2 outputs. Okay, we have 2 outputs. So let's say we want to detect 2 types of objects on the image. So this is a very, very simple data set, which specifies one line in the middle. See, these are all zeros, then these are ones and zeros, and the other one which has some kind of a different pattern. And we say that output for this pattern, we are creating data set manually here, just for demonstration purposes. We said the output for the first one is 1, 0, and for the second one is 0, 1. Next, we want to set the maximum error threshold. You remember that we, in the beginning, entered the dialog. We specify 0.001, and again, we just invoke this learn method and provide the data set to the network. See, the same principles that we use for multi-layer perceptron, and that's the idea of the whole Neuroph framework. It uses the same simple public API for all types of neural networks, and it is very easy to use. And let's start this one to show you the result. It is not some very impressive result, but it is interesting to see. Okay. You see this message done training, so the network has learned these 2 simple patterns, and it says that it has finished training. Now, after it has finished training, we took those 2 feature maps layer here. Okay, these are 2-dimensional layers. There is a class in Neuroph called layer. It is a layer of neurons, and there is also layer 2D. It's 2-dimensional layer of neurons. We took those 2 layers and put them into weight visualizer. What we are building in Neuroph Studio is we want to visualize what's going on in your network in weights, and these are 2 patterns that the network have learned from this simple data. So these 2 are obviously meaningless, but it is interesting to see that the network has learned different patterns. This is what it is using as a kernel to detect, to make a distinction. Actually, it is just making a distinction between these 2 inputs. So, next thing I'm going to show you how to create a convolutional network inside Neuroph Studio. Okay, so we are creating a new Neuroph project. And we go into File, New. We say we want some new Neuroph component. We say we want a new neural network. Say Next. And here we select type of neural network that we want to create. As you can see, Neuroph supports a bunch of different types of neural networks. And here the last one is convolutional network. Okay. So the first thing that Neuroph asks is to enter the size of the input layer. So let's use the same example. We want to enter, have input layer 5 times 5 pixels. After that, we want to add one convolutional layer, and we say we want 2 maps, and we say we want kernel width 3 times 3, and then we can say, okay, we want this 2 neurons in output layer. And what happens is that Neuroph created this convolutional network. Now, the visualization of this network is not how it should look like, because this first layer should be 2-dimensional. It's still visualized into 1-dimensional layer, but in its structure under the code, it is 2-dimensional layer. So after this, we can import a data set. Say we want a new data set. Select Neuroph, select data set, and we say we want 25 inputs, right? and 2 outputs. We want to load it from file, check file, and select this file prepared for, let's see, we import, it is the same data set that we have showed in code, and again, we just drag and drop code and hit training. So it is very simple, but for some reason it won't work. Okay, let's see if it is going to finish. So there's not really much to see even when it trains. It just shows that learning graph, it usually finish it in a very small number of iterations. Okay. So before we move forward, I would like to ask you, are there any questions? Yes?
I would like to ask about Neuroph. Is it just for training purposes or it can be used for real analysis? What are performance?
It can be used for real-world applications. To be honest, we are working on to improve the performance of Neuroph, because at the moment it's not using in GPUs. There is an implementation actually of Neuroph that is using GPUs. You can find it. It's a guy from Bulgaria. I think his name is Ivan Vasilev, and I would like to thank him at this occasion for the very nice contribution. You can find the implementation of the same Neuroph API on GPUs. We are also working on parallelizing using Java concurrency API. That will be interesting. I think at the moment convolutional networks are using fork join framework, which probably has, it's not the optimal solution. It does lots of creating threads and things like that. It's not kind of problem that you should use fork join framework. After some research, we figured that out. And the other thing, what we would like to do is create a distributed training. Okay, so when you're doing with some huge data set, you can distribute over the different nodes or parts of data set. Exactly, like MapReduce on there was even a project proposal for Google Summer of Code for MapReduce on Hadoop, but unfortunately the Indian guy never get to finish that. So this was a very basic example. So if you have any questions, so feel free just to interrupt and just raise your hands and ask. So the more realistic example is that MNIST dataset. Let me just see, why is this? Yeah. Sometimes it has memory issues. Okay. Let's stop it. So this is, I'll just find it. MNIST data set is the first data set when people figured out that convolutional network can do something interesting and better than other solutions. You have this link to the MNIST data set. It contains 60,000 training examples of different handwriting for digits. It's digits between 0 and 9, and contains also 10,000 examples used for training. And it is a subsample of the original handwritten digit data set from American National Standard Institute. And the nice thing is that it is pre-processed data set. So you don't have to, you can test different settings in your algorithm without much pre-processing. It is very important because in practice, you are actually doing a lot of pre-processing. For example, we tried doing some check recognition, and you get various types of problems when the checks are not scanned the same way. They have different light, they have different problems, different orientation, and things like that. So that pre-processing step for a huge amount of data, let's say for 60,000 samples, is a lot of work. Also labeling is a lot of work when you have that amount of data. So this is example how convolutional network from Neuroph can be used to deal with this sample. So all the letters are 32 times 32 pixels. We are using convolutional kernel with 5 times 5, pooling kernel 2 times 2, and we have convolutional network builder, which add few layers of convolutional and pooling neural layers. As you can see, this first convolutional has 10 feature maps, so we are kind of looking for which roughly corresponds to 10 digits. We are creating also instance of backpropagation algorithm. It is also a very simple Java class, and you just set different parameters and then you initiate the learning. So I will start this example, but also I must tell you that it will probably take 6 hours to complete. Okay. So you'll see that running one iteration, okay, for learning takes about 1 minute. Okay, so we have after running for an hour, I saw that a rough estimate that it would take 6 hours to complete. When working with some even large data sets, it can take a week. You know, so the computational power is very critical here, and that is one of the reasons, one of the problems when working with neural networks. Okay, let me see. Okay, so also in this package you have this dataset loader, because the format of the original dataset is a bit tricky. You have to figure out it's in raw bytes, and you have specification on this link I provided, but you have a class in Neuroph that does imports all the data in the format that it is easy to use. Also, it is worth mentioning that we are trying to develop the entire workflow. It's not just training network. You have to test it. You have to cross-validate it with different subsets. So we have cross-validation procedure, and what we are doing now is developing statistical tests for classifiers. And our final goal is to provide the environment, the tools, and the framework you can use to customize to deal with the entire workflow. So I think there's not much time left, so I would just like to quickly mention one more architecture that I explained at the beginning. That's Autoencoder. Now imagine having a multi-layer perceptron that has same number of inputs and as the number of outputs, and that you're using inputs as desired target for outputs. Okay, so you're using multi-layer perceptron, saying if you have, for example, 10 inputs, you say you're going to have 10 outputs, and the same values that you have inputs, you are going to use as outputs. And you're going to have one hidden layer, and you're usually going to have smaller number of neurons in the hidden layer. Now, why is that interesting? Because it is in hidden layer, you're actually creating compressed representation of the input vector. Okay, so you're managing to reduce dimensionality, and you're managing to discover maybe somewhat hidden structure of the input vector. Now, interesting thing, these autoencoders obviously can be used as feature extractors, and even more interesting application is to create stacked autoencoders. Now, stacked autoencoders, imagine if each hidden layer of autoencoder is input layer for the next autoencoder. Okay, so you have a number of autoencoders, and you're managing to create better structure and reduce dimensionality. So you can use autoencoders for some kind of pre-training of multi-layer perceptrons, because the main goal with neural networks, basically with any kind of machine learning, is to simplify the data set as much as you can, and by reducing dimensions, that can be very important. So if you want to use autoencoder in Java code with Neuroph, you just call constructor of autoencoder network. That's it, nothing else to do. And if you take a look at the source code of autoencoder class, you'll see that it just extends multilayer perceptron, right? And you just say, okay, use the same number of inputs as outputs and use everything that already exists in multilayer perceptron. So that's why Neuroph is interesting. You can play with it very easily, and using existing components and algorithms, you can easily develop your own. Now, to finish, I will just say what are the typical problems when working with neural networks. Well, because you actually don't know what's going on. What's the meaning of the weights? We have explained the general principle and how it works, but you never know what's actually going on. If it doesn't work, you're not sure why it doesn't work. Do you need more layers? Do you need more neurons? Do you need different kernel size? You just have to do sensitivity analysis, which means guessing, right? If it works, it's the same thing. You don't know why. It's actually the post I recently saw on Twitter, how working with neural networks looks like. It works, why? It doesn't work, why? So that's a big problem. Next, what type of network you should use? How many layers? All those settings. And the one that we already mentioned, it's a long training time, so you need a couple of hours, maybe a couple of days to get something result, and then you can try something else. Of course, there are techniques used, for example, kind of pre-training. You'll use smaller data set and then see if it works, and then if that works, you can try to increase data set and go for a bigger. So, to conclude, we can say that deep learning is a powerful machine learning which solves some of the existing problem with manually preparing data set and eliminates some unnecessary steps. However, it has its own problems, like neural networks in general, and what Neuroph can provide for you is the set of Java classes and nice user interface for building different types of neural networks and deep learning architectures. So this is the direction in which Neuroph will develop. As I said, improving performance, developing new architectures, and providing distributed training and workflow. Of course, problem for potential long training time and guessing architecture are open subject for research. So if you have any questions, please. Okay? Can just be louder so everybody can.
When I want to do feature extension,
Mm-hmm.
I use a technique like principal component analysis. I have a full data set, I do principal component analysis, and I take the most important time dimensions. So I done feature extension.
Yeah.
And pretty much similar when I have a multi-layer autoencoder, right? I'm reducing dimensions, so it's the same principal component.
Yeah. Well, if the principal components works for your problem, use principal component analysis. You don't need to mess with convolutional networks. But if you find some situation or narrow cases where you can't get improvements with the principal component analysis, then you might try to see if that can be solved with convolutional networks. Okay? Huh? Do you think overtraining or? Well, I don't. And this is an example. It is very simple examples, and I don't. I just do the overtraining. But you have another class called cross-validation, and you can cross-validate the neural network. You provide the neural network, you provide data set, and you said how many subsets you want to use, and it runs cross-validation procedure, and it calculates confusion matrix and all the classification metrics. Okay, so So it depends on the problem.
How do you choose the number of hidden layers and the neurons in multilayer?
Well, actually, in the convolutional network, is not that difficult. With multi-layer perceptron, it is difficult because there are some rough. The straight answer is try and see if it works. Okay, but with convolutional network, the number of neurons in each convolutional layer depends of the number in previous layer and the kernel size. So the size of the convolutional layer is always size of the previous layer minus kernel size plus 1. Okay, so if you have a picture of times 5 times 5 and you scale this kernel, you'll get the next layer 3 times 3. Okay, so but open question is how many hidden neurons you need in that output multi-layer perceptron. But there are some heuristics which says number of input neurons plus number of outputs divided by 2 plus 1, but it might work, but also might not in some cases. Okay. So that's the open problem with neural networks. Okay. Yeah. No, I don't have. If there are no more questions. Okay, I can show you a few more links to point out. There is deeplearning.net. It's a site that provides a lot of information about deep learning. Let me see if I have. Yeah? Neo4j. It's different thing. Neo4j is. Yeah. Yeah. There is one which I think it is good. I haven't tried it, but deep learning for J. I think it is a good one. Yeah, I will try to play with it a bit. It is faster. Okay. There is ENCOG, but ENCOG does not support convolutional networks. ENCOG is a very nice framework. It supports different architectures, but because they're using an array-based implementation, just entire network fits into a single array. It is very efficient, but it is very hard to develop more complex architectures. So Neuroph has this nice design, Java API. It has its bad side because of the performance, and what we want to do is to keep the development into the same direction, keep the user friendliness, keep the same philosophy, but try to gain more performance. Because people really like it, and the people who just start with neural network, it is very convenient in what they are used to in Java. So on this side, let me see, I can get this link, deep learning. You have different data sets, so you can try to play with it. And also, I would like to mention that the commercial support is also available for Neuroph. It's a company called Smart4Net. It's a small company. We started recently. Okay. So you can, on this, let's see what to do. It is not connection. Okay, thank you very much for attending the session. If you have any questions, I will.